Okay, so we just completed this problem of how many ways can we deal 5 cards from a deck of 52 cards, we're assuming, where the order does matter. So it will be permutations. We'll move into combinations later. That's where the order does not matter. But for now, the order matters. We had calculated it and seen that it was in the hundreds of millions of possibilities. So it was pretty impressive how many there could be. All right. Now, I want to look at the meaning of this. We want to understand why this works the way it does. So I'm going to draw a little diagram here. We have 52 cards, so I'm going to draw 5 of them. And then we have the rest of the deck. So I'm going to say 47 left. I'm just going to put that in one box. That's the stack that is left after you pick the 5 cards off of the top of it, right? So there are a couple of things about this that we should note. So for these cards, it does matter the order. Okay? That affects how the game will play out, depending on the order in which those 5 cards are handed to us, right? For these cards over here, they never get played. So these are never played or never used, or they're not part of the set of cards that we have. So the order does not matter. Okay, then there's the entire thing. Okay, and we've learned that the deck could have been shuffled before you dealt the cards. Deck had 52 factorial possible orders. Say orderings. Okay, so there were 52 factorial ways that could have happened. Okay, now coming over to this set of 47, the order of this doesn't matter. There were 47 factorial ways to order the deck that's left behind. But we don't care about those 47 factorial ways because it just doesn't matter what order there are. So out of the 52 factorial possible ways of ordering this, we want to divide out the 47 factorial ways that don't matter, okay? And that will leave the order that does matter, the number of possible ways that we could have these 5 cards be played out of a deck of 52. So when we look at the permutations, P52, 5, we have 52 factorial over 47 factorial. So we are looking at the numerator is all of the possible ways a deck could be shuffled. But then we divide out in the denominator the ones that don't matter. Okay, so the 47 cards left behind could be in any order that we want. So we have to divide that out. And we saw the 52 cards could be shuffled in approximately 10. This was, I'll just give one digit of scientific notation. All right, if we did the same thing for 47 factorial, in fact, let me compute that real quickly. Okay, so I did compute that, and it was 2.6 times 10 to the 59th power. And hopefully you know that you subtract exponents when you are dividing. So that ends up being 10 to the 8th power. And if you do the whole thing, it ends up being about 3.1 times 10 to the 8th, which is exactly what you would get if you put P52, 5. In other words, the permutations for 52 objects selected 5 at a time, you will end up with the answer that we have. Okay, so let me just summarize. We want to take the numbers of ways the deck could be organized and divide out the number of ways that the leftovers could be ordered, because the ordering of the leftovers doesn't matter. So that's what the permutation formula is really telling us, right? So hopefully you had a chance to look through example 4 in the textbook. If you didn't, stop this video for just a moment and read through example 4. I just want to go over that quickly. So in example 4 in the text, you have 6 runners in a race. I believe the first question is how many orderings could we finish in? So how many ways could they place? How many ways to place 1 to 6? Okay, so basically you could think of the runners as a deck of 6 cards. We don't know anything about their abilities. We're just calling them runner 1 through 6 or runner A, B, C, D, E, and F. All right, and we're going to figure out how many different ways they could finish. Well, the first place could be filled in by any one of the 6 runners, and then the second place there are 5 left, 4, 3, 2, and then there's only 1 left for 6th place. So that would be 6 factorial ways that could happen. I'll leave that to you. The solution is in the book for that. So it's simply the same as playing all of the cards in the deck and looking at the ways we could organize that. Question B was more interesting. Okay, how many ways to finish, let's say, 1 to 3? Okay, so typically if you're at the Olympics, you have a bronze, silver, and gold medal. We might want to figure out if all the runners are essentially equal in ability. So, we don't have Usain Bolt's where the probability that he'll win is 99% likely. We're going to just assume they're all the same. We just want to figure out the different numbers of ways. We're not figuring out a probability here, just the numbers of ways they could finish. We're not saying which one is more likely. So in order to do that, that would be, we would have 6 runners placing, but we'd have 6 total runners. And in the 1, 2, and 3 spot, the order matters. So the key thing is understanding when order matters and when it doesn't. In the 4, 5, and 6 spot, order does not matter. Okay, so we have 6 things where the order matters for the first 3, but not for the last 3. It's kind of like the cards that are left in the deck that don't get used. Nobody cares about who came in 4th, 5th, and 6th, I'm sorry to say. They all just did not get medals. So the answer to this one would be the number of permutations for 6 elements, 6 objects. They're not really objects. So 6 members of the set taken 3 at a time. So that would be 6 factorial over 6 minus 3 factorial. This one we can do pretty easily by hand. So that would be, if we look at that, that's 6 factorial over 3 factorial. So we could rewrite the numerator as 6 times 5 times 4 times, and then stop at 3 factorial because the denominator has a 3 factorial. Those 3 factorials will cancel out, and you're left with 6 times 5 times 4, and that's relatively easy to do. 6 times 5 is 30, times 4. There are 120 different ways for those 6 runners to place 1st, 2nd, and 3rd. Remember, we're not worried about 4th, 5th, and 6th anymore. Whereas up here, we were worried about all 6 places. So 6 times 5 times 4 is the 120 we just got, all right? But then we would have another 6 ways that these folks could finish up. So this would be times another 6. So that, I believe, is 720 ways that we could count places 1 through 6. So the ways to finish 1st through 3rd are much more limited than the number of ways to finish 1st through 6th, because when we don't worry about the order of the last 3 places, we divide that 6 out of, if you look at the denominator here, the denominator in fact is 6. So we divide out 6 of the, divide the total number of outcomes by 6 because we don't care about the order of the last 3 places. Okay, so I think that would work pretty well. I think that actually that's everything that I wanted to cover in this video. So enjoy the homework problems.